Good morning or afternoon, depending on where in the country you're joining us from. Rob and I will be presenting a project on the Upper Arkansas River near Granite, Colorado, that was over a decade in the making. The construction of the Granite boat chute was a collaborative effort that replaced a diversion dam and intake, improved navigability, and reduced risk to river users and municipalities. We'll be walking you through the project from initial concepts through completion to show you the value of partnerships when rivers need to be managed to work for a diverse group of stakeholders. I'm Brian McCormick. I'm a water resources engineer for Colorado Springs Utilities and was the technical lead for this project. The project was completed by the cities of Aurora and Colorado Springs, Colorado as partners in the Homestake Water Project. I've had a varied career, including academia, consulting engineering, and work in local government, but all having a common denominator of water. As a Virginia Tech graduate, it's nice again to visit Richmond. All right, that was probably too soon, so I'll hand it over to Rob.
Hi, I'm Rob White, and during the development, design, and construction of this project, I was working for Colorado Parks and Wildlife as the park manager of the Arkansas Headwaters Recreation Area, hereafter referred to as the AHRA. I recently retired from Colorado Parks and Wildlife after a 31-plus year career, and I'm excited to be able to share the Granite Recreation Site story with you. For those of you not familiar with the AHRA, the state park is located in a mountainous region of central Colorado. The AHRA itself stretches 152 miles from just below Leadville, Colorado, to Lake Pueblo State Park, and sits at an elevation that ranges from approximately 9,500 to 4,500 feet. The project location itself is just below Granite, Colorado, at River Mile 16 in a stretch of Class 3 to Class 5 water. The Granite diversion was one of 4 diversions that was identified for improvement in the early to mid-2000s, and due to the nature of the terrain, was the most complicated project undertaken to date. And finally, I'd like to note that AHRA is cooperatively managed by Colorado Parks and Wildlife, the BLM, and the U.S. Forest Service.
All right, so why are the cities of Aurora and Colorado Springs working in the Upper Arkansas River? Simply, the majority of the population of Colorado is concentrated along the Front Range or the eastern edge of the Rockies, and the majority of the water is along and west of the Continental Divide. The cities partnered in the 1960s to develop a project to move water from Homestake Creek in the headwaters of the Eagle River across the Continental Divide to the growing cities. The Arkansas River diversion near Granite was constructed as an intake to the Otero Pump Station. In the 1980s, the intake pipeline was extended to Twin Lakes to take advantage of higher elevation and reduce energy costs. The Arkansas River diversion, now a secondary intake, was known on the river as the Granite Dam. Prior to the project, the Granite Dam was no longer a reliable point of diversion due to sedimentation and debris issues and required whitewater boaters to portage in order to continue downstream. This photo looks upstream at the Granite Dam prior to the project. The dam was originally a rock-fill dam with an articulated concrete block cap. Steel sheet pile was used to reduce flow through the structure, and the concrete blocks were tied together with loops of rebar. Additionally, the toe of the rock fill was anchored with steel cables. When the dam deteriorated, as anything eventually does in a river environment, these materials trapped debris and posed risk to river users. For the geomorphologists in the audience, the rock-fill dam eroded into a nice series of step pools. But here are the details that we found when we diverted the river to begin construction. The steel cables used to anchor the structure, as shown in the upper left photo, when exposed, trapped debris, shown in the upper right photo. And as a mediocre kayaker, I can attest that boaters and swimmers behave like debris in the river. Rebar, on the lower left, posed an entrapment hazard and a puncture risk to inflatable craft. And the erosion at the crest of the dam, which you can pick out in the lower right, exposed the steel sheet pile, leaving a sharp edge and a short pour over at the top of the dam. Many people were interested in improving this situation.
As you can see, the project partners included a diverse stakeholder group. The water providers were primarily interested in a reliable water supply and risk reduction. Colorado Parks and Wildlife was interested in navigability, risk reduction, recreation, user safety, and the fisheries. The Colorado Water Conservation Board was interested in advancing the Colorado Water Plan, which is balancing competing demands on our water resources, both the consumptive and non-consumptive uses. And finally, river interests, boaters and anglers, were interested in recreation, fisheries, access, and risk reduction.
Design development began in the mid-2000s when the cities assessed the condition of the homestake system. The initial design focused on simple repairs and stabilization. As the design and the partnerships evolved, we considered a boat chute down the center of the structure, and then a separate drop and pool arrangement. This progressed to our final design, shown here, and eventually to the completed project. And that was a whirlwind tour that we just went through in a few seconds. To put it in perspective, it took us about 15 years to get us from that original concept to completion. I learned that these projects take a lot of time and that the relationships between stakeholders are critical to keep things moving forward effectively. A critical piece of the process was to solve problems on paper prior to getting in the river. To ensure that the final project would meet the owners and the stakeholders' risk tolerance, and to minimize adjustments or rework needed in the river, we used a tiered design process, which culminated in a scaled hydraulic model. We began with desktop hydraulic calculations, progressed through two-dimensional computer modeling, and eventually built a 1/12 scale model of the project, as shown in the upper right. Each step provided the starting point for the next level of design. The scale model was adjusted in the lab to improve performance and then LiDAR scanned for use in creating the construction plans. The photo in the upper right shows the intake structure. We adjusted the upstream corner of this structure by 4 inches in the model, or about 4 foot at full scale, to improve performance. This was something that could not be evaluated in the computer model, and looking at the size of the partially completed structure would have been difficult and very expensive to adjust after construction. This improvement and the potential cost implications of having to make this at full scale alone justified the cost of the scale model. These details give you a sense of what goes into construction of a model like this. The frame and ground contours are set with plywood, as shown on the upper left. The tubes are manometers used to measure water levels or depths at points of interest. The intake was designed to take water to allow us to evaluate debris management, sedimentation, and user safety. And the yellow on the yellow face of the intake on the lower right shows that adjusted front face. The model was evaluated at varied flow rates from a base flow of around 200 CFS up to about a 200-year return period, or about 4,000 CFS. Low flow was representative of spring and fall spawning periods for brown and rainbow trout and was used to evaluate fish passage and the low end of whitewater use. 700 CFS is a typical summer recreational flow, and then the higher flows were used to evaluate scour protection and stability of the completed project. The model allowed us to improve wave shapes and alignment in the boat chute. This image is one of the boat chute drops based on the computer model design. Note that the jet is turning down and creating a strong and possibly retentive hydraulic. There's also air entrainment. And air does not scale well. So if you see any air in the scaled model, you can expect to see a lot of air entrainment and turbulence at full size. We wanted the wave shape to be flushing and look more like this. By lengthening the apron of the drop, we were able to better support the hydraulic jump and create the desirable green tongue and a flushing, non-retentive hydraulic. So our final design, pardon me, starts with a weir. At the top, this maintains the headwater for the intake. You see the intake and pipeline over on the left bank. River right is our spillway channel. This is constructed of 3 to 4 foot diameter grouted boulders for stability and to reduce entrapment risk. On the edge of the spillway is a weir and pool fishway for upstream migration of trout, and we have visually observed target species making their way upstream through the project. River left is a drop and pool boat chute consisting of 6 2-foot drops and recovery pools, also constructed of grouted boulders. The drop faces were made from concrete to allow passage at lower flow and to produce repeatable hydraulic performance. To facilitate construction, a temporary bridge was built downstream of the project, and the construction access roads used during construction were turned into portage pathways and river access at completion. As with any river construction, construction was challenging. Whitewater users had to portage during construction. We learned that the best way to end a drought is to start a big river project. In the summer of 2019, we experienced very high runoff from a large snowpack. We had half the project, or the spillway side, completed at this point, and we were able to divert the river onto the completed work and test it with the equivalent of a 100-year runoff event because the flow was concentrated onto one side of the project. In the absence of high flow, the Arkansas is a snowmelt-dominated system at about 9,000 feet in elevation. So if there wasn't runoff, there was ice and snow. And to give you a sense, in the lower right, give you a sense of the dewatering involved, you can see the extent of the cofferdaming used, as well as we were able to use some of the existing intake plumbing to keep the work area dry and bypass the river. All right, so this photo shows water on the boat chute for the first time, and you can see some of the cofferdam used to concentrate flow into the boat chute. This allowed us to artificially increase flow for performance testing. And just as we made evaluations and adjustments in the scaled model, the full project was evaluated and tested prior to opening the site for public use. The largest adjustment we made was to add an additional drop for grade control downstream of the structure. Combination of the disturbance from dewatering and cofferdam construction and scour from the high flow in 2019 left us with less tailwater than desired. The drop off at the end of the boat chute was taller than desired, and the resulting hydraulic was stronger and off of the stabilized portion of the riverbed. So an additional structure, as shown in the lower right, was built downstream to raise tailwater and transition to a stable reach of the river. The project was tested by trained, properly equipped whitewater users to ensure that hydraulic performance was as expected and risk tolerance were met. In the R2 are Mike Harvey and a coworker from Recreation Engineering and Planning in Boulder, Colorado. You can tell they're having a very rough day at the office. Do note that the sun is out and shining in this video. Because just 2 days later, we had an invitational test event for local whitewater boaters to allow them to experience the project and provide feedback. And I want to thank our volunteers for braving our first major snowstorm of the season to evaluate the project and help us understand how it was working for them. So here's where Mike Harvey is earning his fee. Just as we tested the intake in the scale model, we ran water through the intake to evaluate potential for impingement of debris, which includes boaters or swimmers. The intake is running at an equivalent to full capacity of the pump station, or 60 CFS per bay. The large grade area results in a low approach velocity. This, combined with the sweeping velocity, makes it very difficult for our swimmer to even temporarily stop at the intake. And this type of testing was critical for us as an owner to be satisfied that the completed project met our risk tolerance. Similarly, performance testing included swimming the drops by a swimmer properly equipped with a PFD, exposure protection, and a helmet. But this does clearly show that we achieved the flushing characteristics of each of the drops in our boat chute, and that our swimmer gets dunked, but he does get spit out on the downstream side of each of those hydraulics. All right, back to Rob.
In terms of project feedback to date, one can see from a few of the testimonials noted here that the project has been an overwhelming success, especially from a boater's and angler's perspective. To go from what in essence was a mandatory portage and fishery barrier to a Class 3 boat chute with a functioning fish ladder in 1 year's time is simply fantastic. To wrap up our presentation, I'd like to thank all the project partners noted here, especially the City of Aurora and Colorado Springs Utilities, which makes up the Homestake project, the staff at CPW, AHRA, the BLM, and USFS, the Colorado Water Conservation Board for the critical funding that they provided, and especially the volunteer testers who underwent some pretty horrific conditions during the snowstorm to make sure that the project would work well for everyone.
Thanks, Rob. At this point, we'll open things up for questions and discussion.